In this episode, we will talk about, does reinforcement learning really incentivize reasoning capacity in LLMs beyond the base model?
It's a really interesting question.
Yeah, we're digging into some research that kind of challenges what a lot of people think about how these big AI models learn to, well, reason, especially for tricky stuff like math or coding problems.
hmm And you hear a lot about models like OpenAI's O1, DeepSeek R1, Kimi 1.5. These models known for being pretty good at reasoning.
Exactly. And the common story is that this technique, reinforcement learning with verifiable rewards, let's call it RLVR for short. That's the secret sauce, right?
That's definitely the prevailing idea. You train the model using rewards. It can check automatically, like, did I solve the math problem correctly? Or does this code actually run without errors?
Makes sense.
And the assumption is this process helps them learn reasoning that goes beyond what they could do initially, in their basic form, the base model.
So they get a reward for thinking, well, they should learn to think better, maybe even in new ways.
Sounds logical, yeah.
Okay, but this deep dive, it's really going to push back on that idea. The central question we're tackling is, does RLVR really give these models new reasoning powers?
Or
Or is it mostly just making them better, maybe more efficient, at using the reasoning skills they already had?
Right. Is it adding new tools to the toolbox or just teaching them to grab the right tool faster?
That's a good way to put it. And the researchers here used a pretty clever method to get at this.
Yeah, they focused heavily on something called the pass at K metric.
Okay, pass it K. Let's break that down a bit.
Sure. So pass at K is basically a way to measure if a model can solve a problem if you give it K chances or K attempts.
Ah, so not just the first try.
Exactly. Pass at 1 is just that first try. But here they looked at what happens when K is really large, like hundreds, maybe even thousands of attempts.
So you're giving the model tons of shots at the problem.
Right. And using a really big K gives you a much better sense of the model's absolute boundary, what problems it could eventually reason its way through, even if it takes many tries.
Okay, that makes sense. It's like, if the raw potential is there in the base model, maybe it just needs enough chances to find the right path.
Precisely. It's a more rigorous test of underlying capability.
So what happened when they actually did this with the deep sampling? This is where it gets juicy, right?
It really does. The results were, well, quite surprising, I think. They found that, yes, the RLVR trained models were better at the start, higher pass at 1, meaning they got it right more often on early attempts,
As you'd expect.
as you'd expect.
Yeah.
But when they cranked up K, let the models generate many, many samples, the original base models started closing the gap.
No way.
Yeah, and in a lot of cases, the base models actually caught up to, or even surpassed, the performance of the RL-trained models at those large K values.
Wow, okay. Across different models.
Across different model families, they looked at Llama 3.18b, various sizes of Kin 2.5, and across a whole suite of benchmarks, things like GSM-8K, Match 500 for math.
The tough ones.
Yeah, and Olympiad, AE, AME. Also coding benchmarks like Live Code Bench, Human Evil, plus Tuin MBPP, plus even visual reasoning like Math Vista.
So this pattern was pretty consistent then, base models catching up with enough tries.
Very consistent. Figure 2 in the paper lays it out visually. You see these performance curves.
Okay.
The RLVR model starts higher, but the base model's curve often climbs more steeply as K increases, eventually meeting or exceeding the RLVR model.
That's wild. So the base model can solve problems that people thought only the RL-tuned models could handle. It just needs more chances.
It strongly suggests that, yes, they even did manual checks on the reasoning steps, the chain of thought, or COT,
Ah, okay.
and found that often the base model did produce at least one correct reasoning path within those many samples.
So it wasn't just guessing lucky numbers. The reasoning potential was lurking in there.
Seems like it.
Yeah.
Which leads to the next big finding.
Which is, if the base model has the potential, what is the RLVR actually doing? Why does it perform better initially?
Right. The research suggests RLVR mainly boosts what they call sampling efficiency.
Sampling efficiency, okay.
Think of the base model having this huge space of possible ways to try and solve a problem. Some paths are right, lots are wrong.
A big search space.
A huge search space. RLVR training seems to bias the model. It learns to favor the paths that are more likely to lead to a reward, a correct answer.
Ah, okay. So it steers the model towards the good paths it found during training.
Exactly. Figure 1 in the paper has a nice little diagram for this. The base model explores widely, sometimes finds the green correct paths. The RLVR model focuses its search much more tightly on paths it thinks will work. the rewarded ones.
Making it more direct, more efficient at finding those specific solutions.
Precisely. That's why you get better pass at one scores. It hits those known good paths faster. But there's a trade-off,
There's always a trade-off.
isn't there? This efficiency boost seems to come at the cost of exploration. By narrowing its focus, the model might actually miss other correct reasoning paths that the base model, with its wider search, could eventually find.
So improved efficiency, but maybe a narrower overall scope of what it can solve.
That's the second key finding, exactly. The RLVR might actually shrink the reasoning capability boundary compared to the base model's potential at very large K.
And figure 1 shows that too, right? The pass at 1 goes up with RL training, but the pass at 256, the performance with lots of samples, can actually go down.
Yes, that declining pass at 256 score as RLVR training progresses really highlights that shrinking coverage. It's optimizing for known paths, but potentially losing the ability to find others.
Okay, that makes sense. Did they look at the actual reasoning patterns themselves?
They did. They used perplexity analysis, essentially asking the base model how likely or surprising the reasoning steps generated by the RLVR model are.
So if RLVR found a truly new way to reason, the base model should find it surprising, low probability.
That's the idea. But the analysis showed that the reasoning paths the RLVR models used were already quite probable, or had considerable probability density, according to the base model.
Which suggests
It suggests RLVR isn't teaching fundamentally new reasoning patterns. It's amplifying or making more prominent the patterns already latent within the base model.
refining, not inventing.
That seems to be the case.
Okay. Now, there are different ways to do this RLVR training, different algorithms. Did the specific algorithm matter much?
Good question. They tested quite a few. PPO, that's Proximal Policy Optimization, GRPO, Reinforce plus RLOO, which is reinforcement learning, with Leave One Out, Baseline, Remax, and DPO.
A whole bunch of them.
Yeah, the common ones. And while there were, slight differences in performance here and there,
Sure.
the fundamental limitation was consistent. None of these RLVR methods seem to significantly push the reasoning boundary beyond what the base model was capable of at high K.
So the ceiling was kind of the same, regardless of the specific RL tool they use.
Pretty much. They introduced a metric to capture this, the sampling efficiency cap, or ASE.
Delta SE, okay.
It basically measures the gap between the RL model's quick performance, pass at 1, and the base model's ultimate potential, pass at 256.
How much better the RL model is initially compared to the base model's best possible score.
Right. And Figure 7 in the paper shows this gap remained consistently large across all the different RL algorithms.
Implying that none of them were fully closing that gap and unlocking the base model's full potential?
Exactly. It suggests current RL methods are good at boosting efficiency, but maybe not at expanding that fundamental reasoning scope.
Were there any notable differences between algorithms even if the main conclusion held?
Some minor ones. They noted, for example, that DPO sometimes got slightly better pass at 1 scores, but needed a lot more training data.
Okay.
And Remax, another method, generally seemed to perform a bit lower overall compared to some others in their setup.
Yeah.
Again, the core finding about the boundary held.
Got it. So RLVR seems limited by the base model, but the paper contrasts this with another technique, distillation. How does that fit in?
Yeah, this is a really crucial point they make. There seems to be a fundamental difference between RLVR and distillation.
How so?
Well, as we've discussed, RLVR appears to mostly refine existing knowledge and reasoning within the model. Distillation, on the other hand, involves training a smaller student model to mimic a larger, more capable teacher model.
Learning from a better model.
Right. And through that process, the student can potentially acquire genuinely new knowledge or reasoning strategies that were present in the teacher, but not in the original base student model.
So distillation can potentially expand the reasoning scope beyond the base model's limits.
The evidence suggests yes. They show an example using DeepSeek R1 as a teacher to distill knowledge into a Quinn 2.5 math model.
And what happened?
Figure 6 shows it clearly. The distilled model's pass at K-curve is consistently higher than both the original base Quinn model and an RLVR trained version of that same Quinn model across all values of K.
Wow. So distillation really did seem to transfer superior reasoning ability, pushing past the base model's apparent limits in a way RLVR didn't.
Exactly. It highlights that how you train matters immensely for whether you're just optimizing existing skills or potentially adding new ones.
That's a very important distinction. Did they look more closely at which problems the different models could solve?
They did. They compared the specific sets of solved problems on benchmarks like AME24 and LiveCodeBench.
Yeah.
Tables 4 and 5 show the results.
In.
The pattern generally held. The set of problems solvable by the RLVR trained model was largely a subset of the problems solvable by the base model, given enough sampling attempts, large K.
Reinforcing that idea that RLVR isn't unlocking fundamentally new problem types, just making it easier to solve ones the base model could potentially solve anyway.
Precisely. And this ties back to the perplexity analysis, too. The RLVR solutions look probable to the base model.
Right. But one question people might have: when the base model solves these hard problems at very high K, is it really reasoning or just getting lucky, like finding the answer through brute force?
That's a fair question. The researchers address this by manually inspecting the chain of thought outputs for challenging math problems, particularly from GSM-8K and AM24.
And
They found that generally, the solutions found at large, KL, did stem from at least one valid reasoning path, not just random flukes.
okay, so it wasn't just noise producing answers.
It seems not. They even took steps to filter out potentially guessable problems from AUP-A24, and Figure 9 shows the same overall trends held even on this harder, filtered set.
So the evidence seems pretty solid that RLVR is more about efficiency than expansion. Do they offer ideas on why RLVR might be limited this way?
They touch on it. One likely factor is just the sheer scale of the action space in language models is enormous. Think about all the possible words or tokens the model could generate next at every single step.
It's astronomical.
Right. So for an RL algorithm to explore this space effectively and stumble upon truly novel, complex reasoning patterns purely through reward signals might be incredibly difficult.
Especially if it starts from a base model that already has strong tendencies or priors.
Exactly. RLVR relies heavily on that pre-trained base model. The base model provides a good starting point, generates plausible text, gets some rewards, which guides the learning. But those same initial priors might also constrain the exploration, kind of anchoring the RL process to the reasoning styles already embedded in the base model.
So the foundation is also a potential boundary.
That seems to be the implication. It helps get started, but might limit how far you can go in fundamentally new directions with just RLVR.
Okay. So let's try and wrap this up. The main takeaway from this deep dive seems pretty clear.
I think so. Reinforcement learning with verifiable rewards, RLVR, it's definitely useful. It makes models better at getting the right answer, especially quickly for tasks needing reasoning.
It boosts that sampling efficiency we talked about.
But the evidence strongly suggests it primarily refines and optimizes the reasoning abilities that were already there in the base model.
It doesn't seem to fundamentally expand the scope of what the model can reason about, beyond the potential the base model already possessed, even if inefficiently.
Exactly. The reasoning boundary of the RLVR trained model appears tightly linked to, and perhaps even slightly constrained by, the capabilities of its base model.
And the big implication there is, well, if we want LLMs to achieve truly new levels of reasoning, to significantly surpass their base models, just applying current RLVR techniques might not be the whole answer.
It might be insufficient on its own to really push the frontiers of reasoning.
Which leaves us with a really provocative thought, doesn't it? If RLVR, as we currently understand and use it, hits this kind of ceiling, what comes next?
That's the million-dollar question, isn't it?
Yeah.
What new paradigms or approaches are needed to unlock truly novel, emergent reasoning in these systems?
Maybe better exploration methods for RL, different kinds of rewards or training objectives.
Perhaps. Or maybe more sophisticated ways of combining techniques, like combining distillation's knowledge transfer with RL's optimization in new ways.
Lots of open questions. It definitely feels like we're still figuring out the best ways to genuinely enhance AI reasoning.
Absolutely. This research adds a really important piece to that puzzle, highlighting both the strengths and the potential limitations of a very popular approach.
Indeed. And for anyone listening who wants to really get into the nitty-gritty details, the researchers have a project page with the paper and more info. You can find it at limit-rlvr.github.io.
Definitely worth checking out if this topic interests you.